Hello everyone, I'm Manish and welcome to this video on AI model optimization. Let's dive into a fascinating challenge. Here's our big question. How can a trillion parameter AI model fit in a pocket-sized device? We'll explore how massive floating point distributions can be compressed into tiny 4-bit integers. Remember, true intelligence lies in the patterns, not just the precision of the numbers. By the end of this video, you'll understand the math and hardware tricks that make this possible. Building on our previous discussion, let's explore the math behind compression. This is where the magic happens. Here, we transition from 32-bit floating point to 4-bit integers. This is the core of compression. This shift is like converting a high-res photo into a vector graphic, simpler but retaining the essential shape. This analogy helps us visualize how we preserve intelligence while discarding redundant data. By mapping vast weight distributions onto a restricted grid and discarding redundant data, we maintain model performance while preserving intelligence. Now, as we wrap up our exploration of model compression, let's connect the mathematical foundations we just covered to real-world hardware implementation. Notice how modern NPUs are physically engineered for low-bit operations. These specialized processors directly support the quantization techniques we discussed, converting floating point weights to integers without losing critical intelligence. This hardware-software synergy is crucial. When chip architectures mirror our compressed model designs, we achieve maximum efficiency, exactly what we need for practical AI deployment. Looking ahead, this convergence means powerful AI will soon run seamlessly on everyday devices. As Mia noted earlier, this transforms smartphones and IoT gadgets into intelligent assistants without cloud dependency. Thank you for joining this journey through compression mathematics and hardware optimization. You now understand how quantization bridges theoretical models and real-world applications. See you in the next lesson where we'll explore neural architecture search.